In general chemistry courses, it's very common to treat delta S for a reaction as a constant and say that it doesn't vary with temperature. So let's check and see if that's reasonable, and then look at a real case to see how much of an approximation it is. Okay, so students are always confused by this because if we think about this, we know that if we look at the entropy of a single substance as a function of increasing temperature, say a liquid, we know that it has to go out. If you add energy into a system, you're going to increase the number of microstates, and that's going to increase the amount of entropy. Now, of course, if you have something like a gas, that should be also true. So if we had a liquid or a gas, they would both be increasing entropies with temperature. However, if we're looking at delta S, so let's imagine we were looking at delta S of fusion. That's the gap between the entropy of the liquid and the gas. And we can see that that gap might not be constant, but it's going to grow at a rate smaller than the individual entropies do. In other words, if the two entropies are growing with temperature at a rate that's similar, the gap between them will grow very slowly. So let's look at a concrete example of this. Let's look at this in the context of a chemical reaction. So here we've got dinitrogen tetroxide, and it's going to split apart into two nitrogen dioxide molecules. So let's look at the entropies of those two molecules involved in the reaction, see how the entropies of the individual molecules change with temperature, and then how the entropy change for the reaction changes as a function of temperature. So first, we've got this little chart. We've got two chunks of data. We look up the third law entropies for the compounds. That's the absolute entropies for the compounds at 25 degrees C. And we see that for dinitrogen tetroxide, its entropy is 304.3 joules per mole per Kelvin, or for nitrogen dioxide, it's 240.1. Okay. So I used a calculation that is sort of beyond the scope of general chemistry. You can ask me about it if you're interested, to calculate what the entropies would be at a higher temperature. For dinitrogen tetroxide, the entropy at the higher temperature, 55 degrees C, is 311.7. So indeed, as we expect, if we go to a higher temperature for a single substance, its entropy increases. For nitrogen dioxide, it goes from 240.1 to 243.7. So it has an entropy increase as well. So obviously the entropy of an individual substance is not constant with temperature. It increases if we increase the temperature. But what about the delta S for the reaction? So let's figure out what delta S is for these two different temperatures. So delta S for reaction is just products minus reactants. We have to make sure that we also incorporate the coefficients when we do this. So it's 2 times the entropy of the products minus the entropy of the reactant. Okay. And we have to make sure, of course, we look up the entropy for the correct physical state. So we've got the entropies already. So let's calculate both of them. So delta S at 25 degrees C. Just plug in the numbers from this table over here, and we get delta S for the reaction. It's 175.9 joules per mole per Kelvin. If we do the same calculation with this data at 55 degrees, we end up getting a delta S for the reaction of 175.7 joules per mole per Kelvin. So if we look at these results, we can say that saying that delta S does not change for reasonably sized temperature increases is actually a really good approximation. We didn't see any difference at all until we got to the fourth significant figure. So even though the entropy does change significantly as we increase temperature, the entropy change for a reaction is often approximately constant.